Okay, so I'll start now. Hello everyone. I'm Eleanna, and I was an AstroCamper in the year 2020. And this was also the year that COVID hit, so it was pretty unfortunate. But yeah, here I am now. And I'm going to talk to you today about my bachelor thesis project, which is entitled Probing Fundamental Physics Using Compact Objects. Um, so first I'm going to just set the stage, some introductory stuff about scalar fields, couplings, and grand unified theories, and also compact objects. And then I'm going to move on to the actual research, the methodology we used, and the results we obtained for both compact objects. So beginning with fundamental interactions and couplings, as we all know, there are four fundamental interactions. We have strong, electromagnetic, weak, and gravitational. The first one is responsible for the nuclear structure and stability. And then we have the electromagnetic interaction between charged particles and gravitation, which is interaction between particles that have mass. And then we have the weak interaction, which is between interactions involving leptons. So examples of leptons which you may know are electrons and neutrinos. So each fundamental interaction has a coupling that relates to the strength of each interaction, which you can see also at the table at the bottom. And this is the symbolism for every coupling, the strength in SI units, and also the relative strength and the range of the interaction. And these couplings, so the strength of the interaction, also run with energy. For example, the fine structure constant, which is the coupling of the electromagnetic interaction, which I have denoted here as alpha, runs with energy, so it changes. So now we also know that the standard models of both cosmology and particle physics aren't all-encompassing theories, so they can explain everything we observe and measure in our experiments. So physicists have been trying to figure out ways to combat these issues and also improve the models that we already have. And one way to resolve some of these issues is to include what we call cosmological scalar fields, which are symbolized with the letter phi. And scalar fields are very simple to use and also very effective to use in theories. And I think the most important thing is that they've also been experimentally proven to exist. For example, the Higgs field. As you can see here, this is a picture from the CMS and ATLAS experiment at CERN. And these experiments actually prove the existence of the Higgs boson and thus the Higgs field. So what cosmological scalar fields do to models that we use them in is that they induce spacetime and local variations of the couplings. So for example, a coupling can vary both in energy and in spacetime as a result of these fields. Now, experiments have also proved at high energies that there is a unification of the electromagnetic and the weak interaction. And this happens at about 100 GeV. And this is the equivalent in joules for if you don't know the equivalent. And this actually got theorists thinking about what if all fundamental forces could be unified into a single force. And then many models emerged, theorizing all of that. And a group of these models is called grand unified theories. So grand unified theories, they state that there is a certain point above the unification of the electroweak and strong and weak interactions, where the electroweak line, as you can see here in the figure, merges with the strong line, and it forms a novel unified force. So the parameters that distinguish different grand unified theories are R and S, and these relate to the energy scale at which unification occurs. And also, they influence R and S, they influence the slopes of the strong line and the electroweak line, respectively. So if we combine these two models, we have three parameters, the R and S parameters, which are for the grand unified theories, and also the variation of the fine structure constant, which is induced due to us adding a scalar field to the model. So in my work, I I just looked into 3 specific examples of brand unified theories, and those are the first one, as you can see here, is called the unification case. The second one is the Dilution case, and the third one, which is relatively new, actually, is called the Yubikharov case. And also, because we're dealing with compact objects, we will only consider space-time variations, so no local variations that will confuse the analysis. Now moving on to something that you're likely more familiar with, as Carlos told me. So we're talking about compact objects, so white dwarfs and neutron stars. White dwarfs, as you already know, come from relatively low mass progenitor stars and have typical radii of maybe about 10,000 kilometers and masses that range from 0.6 to 1.38 solar masses. And given these typical ranges, we have really big densities that occur in the interiors of these white dwarfs. And just to give you an intuition of what's going on, it's as if all the mass of the sun could fit into the size of the Earth. And the same goes for neutron stars. They are formed from significantly larger in mass stars, and they are formed during a supernova, a really violent phenomenon. And typical radii for these stars are 10 kilometers, whereas masses are about 1 solar mass. So as you can imagine, these stars have even bigger densities, and these are, again, as if you could fit the mass of the sun to the, I guess, size of a small city, of a medium-sized city on Earth, which is tremendous. So now the question is here of how these stars can actually combat the gravitational collapse of that such big mass. And this is happens due to a phenomenon called degeneracy pressure, and I will talk about that at the moment. So degeneracy pressure is based on a really important principle in quantum mechanics, and it's called Pauli's principle, which states that neutral fermions with the same quantum numbers can occupy the same state. So fermions, if you are unfamiliar with them, some examples are protons, electrons, and neutrons. And for example, for electrons orbiting their atoms, Pauli's principle states that on the energy scale of these atoms, we have a specific number of electrons that can be put in each energy state. So if you can imagine, we had a gas of fermions, so many fermions, and we put them inside a box and we contained them. And we started squeezing this box, so applying pressure and minimizing the volume of this gas. What would happen is that it would reach a critical density, and then Pauli's principle would prevail. And because the distances between the fermions would be too close, this would induce an outward pressure that will stabilize the gas and just stop the squeezing from happening. And this is exactly what happens with compact objects. So they don't have nuclear fission happening, nuclear fusion happening in the inside. They just rely on this degeneracy pressure to keep them from collapsing. So now, moving on to the dynamics of the neutron stars and white dwarfs, we have the Tolman-Oppenheimer and Volkov equations. And these are 2 equations that the first one explains the hydrostatic equilibrium, and the second one is about the mass conservation. So we have 2 differential equations. This is a problem that we solve, and we are looking for 3 unknown quantities, which is the pressure, the mass, and the energy density, which is energy over the volume. It's exactly the same as the normal matter density that you know. So taking into account that we have 3 unknown quantities and 2 equations, we need an additional one. So what we did is the additional one actually is called an equation of state. And this equation of state describes the behavior of matter at a certain state. So I don't know if you have done it in school, but you may know, some of you may know the equation of state of an ideal gas, which is this one I have in the brackets here, but if you don't know it, just forget about it. So the easiest case of an equation of state is in analytical form, and it's called the polytropic equation of state, which is this one that you can see right here. It relates the pressure with the energy density, where K, which is the polytropic coefficient, is a function of the mass of the electrons and the mass of the protons. So this is really important, and just note that. And apart from this, there aren't any other analytical equations of the equation of state. So we rely on numerical equations of state. So these are numerical tables, and they need, of course, they need different handling than an analytical equation of state. So we use computational methods to handle them. So after we solve the problem, we combine these two equations with the equation of state, the polytropic equation of state. We get to this really big and terrifying function, which is called the mass radius relation. And if we try to bunch together all these coefficients in the front, we just get to a really simple solution, which is this one. So just to give you an intuition about the differences between numerical and analytical equations of state, the first one is the polytrope, as we said before. And you can see it's a continuous line. It doesn't change. It's just that. Whereas with a numerical equation of state, like the one I have on my right, you can see that there are distinct points. So we don't have a continuous equation of state. We don't have a continuous behavior. We just have points here and there that actually are the equation of state. So now moving on to the actual research. We're going to talk about first about white dwarfs. And what we're going to do is combine the white dwarfs physics that we talked about with the particle physics and cosmology that I stated previously. Then we're going to figure out the mass radius relation and then move into some results. So what this says to us. So we have to think about what varying couplings actually do to white dwarfs. So what effect do these have on their dynamics and their masses and their radii? So what this happens is when fundamental forces, so couplings, vary. Also, the mass and radii for white dwarfs and neutron stars, they shift a little bit from their regular values. And how do we model this? We just use this expression, which is called the Taylor expansion. This is really important in mathematics and physics. And we use that to approximate and perturb the model like we want to. So we take this original mass radius relation that we have. This is the unperturbed normal equation that we use. And if we use this Taylor expansion, we actually get this perturbed mass radius relation, where y here is the perturbation. So we've actually achieved goals 1 and 2, which was to investigate what is the influence on white dwarfs and figure out what is the mass radius relation there. So we can actually, since we found like the general relation for the mass radius function, we can actually take this bracket and just put it as is to the top equations by just changing the units a bit maybe, and then substituting also the masses, the particle masses, with their couplings. And the particle masses, as I told you to remember, were found in this K, the polytropic coefficient. So this is how we implement this and substitute the masses with the couplings. And you can see here that we have two cases, the non-relativistic or low energy limit, and also the relativistic and the high energy limit. And the perturbations here, X and Y, are dependent on R and S, which is the gut model, and also the variation of the fine structure constant. Okay, so now moving on to some results. You can see here I have the mass radius relation for the non-relativistic and the relativistic cases, sorry. And one important thing to know is that on the relativistic case, this is a straight line, and this is called the Chandrasekhar mass limit. So the Chandrasekhar mass limit is the upper mass limit for white dwarfs and neutron stars. Of course, it differs because there are different compact objects that have different physics on their side, but the philosophy is the same. So this is the Chandrasekhar limit for a white dwarf, which is unperturbed, and the blue lines are the perturbed mass radius relation for a positive and a negative variation of alpha. So now you might worry about why is a negative variation of alpha have positive effect on the mass, so it increases the mass. So just think of it, we're going to go with it step by step. So if we have a positive variation of alpha, this means that, as I said before, the strength of the electromagnetic interaction becomes stronger, right? It increases. So what this happens is that also the degeneracy pressure that stabilizes the white dwarf increases as well, right? So we would expect that only by having a scalar field, so only a variation of alpha, that the mass would increase, right? So this doesn't happen exactly, as I said, because we also have the unification model, which has a positive R value. So R, as I said before, relates to the strength of the strong interaction. So a positive R means that we have an increased strong interaction, which also results in increased masses of the individual particles. So because this phenomenon overshadows the phenomenon that is induced by the variation of alpha, we actually get that a positive variation of alpha actually decreases the mass of the star. And this is the explanation of why it's smaller. And then moving on to the dilaton model, we have the same exact effect, just more exaggerated because we have bigger values here. And still, since we have a positive R, the negative variation is again increasing the mass of the star. And also, what we found here is we tried to compare this Chandrasekhar masses that we got with the measurement of the most massive star, a white dwarf, ever detected, which is in the range of 1.327 to 1.365 square masses. And because this is really low compared to this limit for the negative variation of alpha that we saw and we found as a result, we have concluded that this model might be a bit unlikely since we got this measurement and we don't have measurements for more massive white dwarfs so far. And now moving on to the last model, which is the cubic model. Here we see something that's expected because we have a negative R here. So what this means is that the roles are reversed. So now a positive variation induces an increase in the mass, whereas a negative variation induces a decrease in the mass. And again, we see that this effect is more exaggerated because compared to the previous model, this model has just bigger absolute values of RNS. So we've done everything we could on white dwarfs. We've investigated everything. So now we can move on to neutron stars. So we follow here the same procedure. We find the mass radius relation, and then we try to fit in more complex equations of state because a polytrope is not that good a fit for neutron stars. And then we produce the same results and see what this means for different equations of state and different models. So we have proven before, we have derived the mass and radius relations for the non-relativistic, which is here, and the relativistic limit. As you remember, this for the relativistic limit, this was just a straight line. So that's why there's no dependency on the radius. So we try to find a more general relation, right? Not just on the two limits, but also in between and also outside these two limits. So what we did was we interpolated. And what this means is something I'll explain in this using this graph. So imagine that A and B are the non-relativistic and the relativistic limits respectively. And we need to find maybe the mass radius relation in a point B that's between them. And we say that because we assume really small changes of the fine structure constant, so really small perturbations to the model, we can assume that these two limits, the A and B, are connected with a straight line with each other. So this is how we can say that P is on this line connecting A and B. And this is how we actually find this interpolated general relation for the mass radius function. Now, we can do this also for P being maybe at values lower than alpha or at values higher than beta, than B. So yeah, this is how we interpolate and also extrapolate by assuming small perturbations and then assuming a linear relation between the 2 points. And since we have the general relation for the mass radius relation, we can do the same thing that we did with white dwarfs and just take this perturbation and put it here in the end of these 2 Todd equations. So A here is the perturbation for these equations. And as you can see here, the important part is that there is a dependency, of course, on the RS and the variation of the fine structure constant, but there's also a dependency on the equation of state, so the polytropic index here. And this is really important because it says that depending on the mass, on the state of matter on the inside, this perturbation changes, right? But as you can see here, it's pretty obvious that we have K's and N's everywhere, so we have assumed a polytrope, right? But what happens if we try to input in there different equations of state that aren't a polytrope and yeah, we don't know what to do with them? So what we did is we took a numerical equation of state, so a table of pressures and energy densities, these points that I showed you earlier, and we tried to discretize it into steps and fit a polytrope into each of the steps. And now that we did that, we were left with a table of polytropic indices, these NIs, and polytropic coefficients for every step. So this is a pair that was different for every step I. And we ran some tests with the discretization, and we found out, as you can see here from the chart, that of course pure points per step is the best way to go, and it increases the accuracy of the result. Okay, so we did that. We figured out a way to input these numerical equations of state into the model. So now let's look into some of them. So this is the SLY4 equation of state. And as you can see, it's pretty consistent with what we saw with white dwarfs. We see the first 2 models that, again, from a negative variation of alpha, we get an increase in the mass and the radius now, because it's not a single parallel line. And also in the Dilettante case, this happens as well. Whereas in the UV cutoff case, we get the opposite effect, rightfully so, because of the negative R value. So now if we expand that and look into other equations of state, we can see that the only thing that changes is the profile of the mass radius relation. So nothing in the models, nothing in the physics changes apart from the profile of the mass radius relation. And we see again that it's pretty consistent. We have, again, the same results for the unification, the Dilettante, also the UV cutoff model. And then one last one, we also see the same results here as well. And yeah, it's pretty consistent, so everything works out fine. Okay, so just to conclude everything, what we did is we utilized white dwarfs and neutron stars to figure out whether actually fundamental couplings could vary in the universe. And we actually created a methodology to find out the mass radius relation for both of these cases. And then we created a code from scratch to actually handle these unique features of the problem, which is the numerical equations of state or different models that we used in cosmology and particle physics. And then we tried to expand that to different grand unified theories and different values of variation of alpha, and also different compact objects, different equations of state. And what we hope to do in the future is to constrain this parametric space, so the grand unified theory plus the scalar field parametric space, using mass radius measurements from neutron stars. And this has already been achieved with white dwarfs. So we hope to add on to that research, add on to that work. And then one more thing that we can do is to add, on the other hand, constrain the mass radius relations of neutron stars using alpha variation measurements. So these measurements from atomic clocks to give us more accurate profiles for the mass radius relation of such objects. And I would like to thank you, and please feel free to ask me anything you want or repeat anything you didn't listen or wasn't clear. And thank you.